Gauss law of electricity. Now Gauss law states that the flux outward from an enclosed surface is the product of the total charge contained in the enclosure and 1 bata 4 pi and 1 bata epsilon 0. So if we have any enclosure and the charges may be Q1, Q2, Q3, Q4, they are arranged or placed at any place. So total charge in the enclosure will be equal to summation of Qi, and summation of Qi will be equal to algebraic sum of charges Q1 plus Q2 plus Q3 plus Q4, and this summation of charge can be positive, can be negative, and can be zero. So the electrical flux phi E will be equal to summation of Qi divided by epsilon 0. Summation Qi is the total charge in the enclosure. Now the electrical flux can also be written in terms of electrical field. So the electrical flux is scalar product of E dot ds, means ds is the area vector and E is the electrical field. So we can combine both, then phi can be equal to E dot ds. This is equal to summation of Qi into epsilon 0. So by Gauss law we can find the electrical field using the relation E dot ds is equal to summation of total charge divided by epsilon 0. Now summation of charge Qi can be positive. If summation of Qi is positive, means the electrical flux associated with the enclosure will be outward. If summation of Qi is negative, then the electrical field associated with the enclosure will be inward. And if the summation of Qi is 0, means total charge is 0, then the flux outward or inward is not possible and it is equal to 0. The example is when there is a electrical dipole, then the total charge of electrical dipole is 0, so total electrical flux will be 0. If we have a cylinder and place the electrical field, there is no charge inside it. The electrical flux is coming inside in the left and going outside from the right side. So total electrical flux of this cylinder will be equal to 0 because there is no charge. If the cylinder contains two electrical dipoles, then the total charge will be equal to 0. So the electrical flux from this cylinder will also be equal to 0. So we can find the electrical flux by using Gauss law, and by Gauss law we can find the electric flux. Now what is the Gaussian surface? Now Gaussian surface is an arbitrary surface or imaginary surface. Its shape can be spherical, cylindrical or cubic or any type. We will take a Gaussian surface conveniently for the calculation of electrical field. Now we can derive the Gaussian law with the help of Coulomb law. Now we know that Coulomb law, that the charge is Q, it is at the distance r, then the electrical field at that point will be equal to 1 bata 4 pi epsilon 0 Q bata r square, and its direction will be in the direction of r. So if we have an enclosure, its shape may be anyone, and we take a small area ds here, the area vector will be perpendicular to this area and that is in this direction, whereas the electrical field due to this charge will be in this direction. So there is the angle between ds and electrical field is theta. So the electrical field at this point P, which is the center of this area, is 1 bata 4 pi epsilon 0 q bata r square into r cap. Now the angle between E and ds is theta. So the electrical flux passing through this small ds area, dE will be equal to E ds cos theta. So we can substitute d phi E is equal to E ds cos theta, and which is equal to q bata 4 pi epsilon 0 ds cos theta bata r square. We have substituted the value of E, ds and cos theta. So the electrical flux d phi E will be equal to q bata 4 pi epsilon 0 ds cos theta bata r square. Now ds cos theta bata r square, this term is known as solid angle. Solid angle subtended by ds area at the point O, which is where the q charge is placed. Now the total flux from this surface will be by taking the integral sum. So the electric flux due to entire enclosure, which will equal to q bata 4 pi epsilon 0 integral into d omega, where d omega is solid angle. Now so QE will be equal to q bata 4 pi epsilon 0, and the total solid angle subtended will be equal to 4 pi. So 4 pi cancel. So phi E will be equal to q bata epsilon 0. This is nothing but Coulomb's law, where the electrical flux associated with the enclosure in which there is only one charge q, then the electrical flux will be equal to q divided by epsilon 0. Now we will use the Gauss law, the Gaussian surface, to find the electrical field of any body which is charged body. The charged body may be line conductor, may be the sheet of charges, may be spherical, may be cylindrical, any shape. So we can find the electric. So what will be the procedure? We have to take first procedure is we will find the direction of electric field. Then second step is we will draw the Gaussian surface. Now third step is we will use the Gauss law and we will calculate the electrical field. So suppose for the example we take a line conductor or line charge. This is the line charge whose linear charge density is lambda, and we consider two parts at A and at B. The length of both the parts is dl. They are equidistant from O, and we have to find the electrical field due to these two small elements at point P, which is at a distance r from A and B. Means AP is equal to BP is equal to R. The electrical field at point P due to element at A will be in this direction, and its value will be equal to EA will be equal to 1 bata 4 pi epsilon 0 lambda into dl. Lambda into dl will be the charge on this element divided by r square into the direction will be AP. Similarly, electrical field due to the dl length or whose charge is lambda into dl at P at point P will be equal to EB will be equal to 1 bata 4 pi epsilon 0 lambda into dl bata r square, and its direction will be in BP. magnitude of electrical field at point P due to A and B, they are equal, but their directions are different. So we can resolve the electrical field of EA and DEA and DB in the axial direction and perpendicular to the axial direction. In the angle between angle APO is theta, similarly PPO is theta. So the component of electrical field in the OP direction will be equal to EA cos theta and EB cos theta. The component of electrical field in Y direction is EB sin theta and EA sin theta. Since EA sin theta and EB sin theta, they are equal in magnitude but in opposite direction. So the net electrical field will be equal to 0. But dA cos theta and dB cos theta are in the same direction. So the electrical field will be exist only in axial direction, that is OP direction. Or we can say the direction of electrical field will be perpendicular direction to the line charge. So we have find the direction of electrical field due to this line charge, and it will be in the normal direction or perpendicular direction to this line inductor. Now we will, second step is we will construct the Gaussian surface. The Gaussian surface is arbitrary surface, and the convenient arbitrary surface is cylindrical whose length is small l and its radius is r. We have to find the electrical at point P, which is at a distance from the linear conductor or the line charge. Then we are having three surfaces. One surface is cap, upper cap S1, lower cap S2, and the cylindrical S3. The direction of electrical field for S1 is this direction and DS is perpendicular direction. So angle between E and DS for S1 is 90. Similarly, for S2, which is the lower cap, the electrical field and DS are perpendicular to each other. But for the S3 surface, which is the curved surface, the electrical field and DS, they are parallel or they are in the same direction. So now next we will apply the Gauss law. According to Gauss law, the surface integral for S1 E dot ds plus surface integral of S2 E dot ds plus surface integral S3 E dot ds. This is equal to total charge, and total charge in the length L will be equal to lambda into L. Where lambda is the linear charge density and L is the length of the cylinder. So lambda into L divided by epsilon 0. So the surface integral S1 E ds cos 90, since E and ds are at right angle. For S2, similarly E ds cos 90, which are also at right angle, and S3 E ds cos 0, because E and ds are in the same direction, will be equal to lambda L by epsilon 0. So first term is 0, second term is 0, and third term is E ds. Now electrical field at every Gaussian surface is same or constant, so we put it in the outside the integral. Then E surface integral S3 ds. The surface integral of S3 ds will be the entire area of the Gaussian surface. Now Gaussian surface is a slender whose radius is small r and whose length is L. So its area will be equal to 2 pi r circumference multiplied by L. So this will be equal to ds will be equal to 2 pi r into L. So E into 2 pi r L is equal to lambda L bata epsilon 0. L will cancel. So E will be equal to lambda bata 2 pi epsilon 0 1 bata r. Now we multiply and divide by 2, then it is equal to 2 lambda bata 4 pi epsilon 1 bata r. Now its direction will be direction which is normal to the conductor. So electrical field E vector will be equal to 2 lambda bata 4 pi epsilon 0 1 bata r into n cap, where n cap is unit direction in the direction perpendicular to the line charge. So here we see that electrical field is inversely proportional to 1 bata r. So we can draw the graph between the electrical field with respect to the distance from the center of the Gaussian surface or line inductor. Then it is the curve is shown and it is hyperbola. So E is proportional to 1 bata r. E will be equal to 0 when r tends to infinity. So in this way we can find the electrical field due to a line charge at a distance r, and its value will be equal to 2 lambda bata 4 pi epsilon 0 1 bata r into n. Now we take the second problem and we have to find the electrical field due to a uniformly charged sheet, or we can say that non-conducting charge sheet. It means the charge is equally on both the surfaces of the sheet. Now we take this sheet. So if the surface charge density is sigma coulomb per meter square, and first of all we will find the direction of electrical field. Now we take the sheet, we take two areas ds and ds of equal size and at equal distance from its center. This is the axis and we have to find the electrical field point P. Then distance AP is equal to BP, means ds element at A and ds element at B are equidistant from the point P, and let this distance is r. So the electrical field at point A, electrical field at point P due to A will be equal to 1 bata 4 pi epsilon 0 sigma into ds, which is the charge of this small area divided by r square, and its direction will be AP. Similarly, the electrical field at point P due to ds area whose charge is sigma into ds at point P will be equal to B will be equal to 1 bata 4 pi epsilon 0 sigma into ds bata r square into BP. Its direction will be BP. So the magnitude of EA and EB, they are equal, but their directions are different. Therefore, we will resolve the electrical field in the direction OP and y dash. So a point, when we resolve the EA and EB in the OP direction, then its value will be equal to EA cos theta and EB cos theta, both are in the same direction. If we resolve the electrical field EA and EB in y direction, then their value will be equal to DB sin theta and DA sin theta, which are in opposite direction and equal amount. So they will cancel. It means only the electrical field will be in the direction which is OP, which is normally to the sheet. So in this way, we can first find the electrical field direction due to this charge sheet. Now second step is we will have a Gaussian surface. Now we are having at this charge sheet and we have to find the electrical field at point P, which is at a distance r from it. Then we will construct a cylinder whose length is 2r and area of cross section is S. This area A and B both are at the same distance from the sheet. Now the sheet is uniformly charged and it is non-conducting, so the electrical field will be towards right as well as towards left. So we can find the electrical field using Gauss law. Now we will use the Gauss law. Now the charge on this area cross section S will be equal to sigma into S. The electrical field at A and B, that will be at point B. Here it will be in this direction, and the area vector E ds will be also in. So here E and ds are in the same direction. Similarly here the direction of E will be in this direction and the ds is also. So here E and ds both are in the same direction. Now we consider the curved path of the cylinder and the electrical field will be in this direction and ds will be perpendicular. So here E and ds are mutually perpendicular to each other. So now we will apply the Gaussian law. Now according to Gaussian law we will apply for the total enclosure, means for S1, S2 and S3 surfaces. Then phi S1 surface will be equal to E dot ds plus phi S2 surface E dot ds plus phi E dot ds. This is equal to summation of qi by epsilon 0, and summation of qi will be equal to the summation will be equal to the sigma into the area of cross section of this sheet at this area, or the area of cross section of the cylinder. So this will be equal to sigma into S. So we will apply the Gauss law. Then the surface integral S1 E ds cos 0 plus for S2 E ds cos 0 plus E3 E ds cos 90. So for S1 and S2 surface, the electrical flux will be equal to E into ds plus E into ds, and for the curved surface it will be equal to 0. So E ds plus E ds will be equal to S into sigma divided by epsilon 0. Now since A and B are at the same difference, so from the sheet, so the electrical field will be equal at right and left end. So we will keep it outside, it is constant, so it will be equal to E surface integral ds plus E surface integral ds is equal to S into sigma bata epsilon 0. So this will be equal to the total area of the left cap and right cap is S. So E into S plus E into S will be equal to sigma S bata epsilon 0. So this will be equal to twice E S will be equal to sigma S bata epsilon 0. S will cancel. So electrical field will be equal to sigma bata 2 epsilon 0. and its direction will be perpendicular to the sheet. So we will write E vector is equal to sigma bata 2 epsilon 0 into n cap. Now here we see that the electrical field does not depend upon the distance r or the point P. So the electrical field, we can draw electrical field as a variation with the r. It is a straight line and it will be constant. It is independent on r. So in this way we can find the electrical field due to a charge sheet at any point which is close to there. Now we have considered that the charge sheet is of infinite length. Now actually the length of the charge sheet cannot be infinite, and if we have the point P very close to this sheet, then this sheet will behave like a infinitely long sheet. So we can say that the electrical field due to the charge sheet will not depend upon the position of point P, and its direction will be always perpendicular to the sheet.